So thank you all for coming. We had lots of great, lively discussions yesterday and throughout the evening. I really want to thank everyone for participating and really contributing to the discussion. It's been very helpful for everyone involved here. So this is going to be a live demo. So it's going to be very fluid in what we talk about. So if you have questions, scream out or chat online. And I have a few things I plan on doing-ish, but we'll kind of go with the flow of whatever people are most interested in seeing how to do as well. So again, we're very hands-on, very fluid, and we'll try to address the questions that everyone has. With that, we don't need to have that slide anymore. I am just going to mention, in case you haven't done it, we won't be needing to follow along all in the same software because that takes like 2 hours in itself to get everyone installed and everyone having the right software and the right data. So we won't try to worry about that right now, but I will point you to this lovely website, samsxrays.com. It's your place for everything Samware in particular, including the download page for the MicroAnalysis Toolkit. We're now on version 3.09 roughly. It's hopefully easy to install. For those of you who have installed it, congratulations. For those of you who haven't tried it yet, I just also want to point that we have little instructions and descriptions. But when it gets to doing things, if you run into problems, as much as I love everyone's emails of support and complaints, there's also this lovely support forum on samsxrays.com. And there's a lovely whole group dedicated to installation help. And as I can guarantee, as time goes on, there will be other problems that go on with updating and installations. And I hope to have lots of things always posted here to help you figure out how to solve all of your SMAC problems, or at least some of them. So just so you're aware that that exists, it's quite handy. Okay. So I'm just going to run this from my command line on my Mac. Yeah. So the nice thing now is we have switched from a compiled version to a pure Python. So it's easy to use, open source. You can go ahead and edit it and find errors in it and laugh at the way I program. Those comments are not welcome usually, but you can get a good kick out of how I've progressed. This software has been a project that started almost 20 years ago. And it's been developed through a lot of user suggestions, shall we say. Not always complaints, but always suggestions, right? And a lot of the features there are based on what people have asked for, required. And it's always a living thing. So if you do find features that you like or would like to see, I always welcome those emails as well. And then of course, if you do ever decide you're bored and you do look through my code, you will definitely see my programming skills as they were in 2005 compared to how they are today. And they've maybe gotten worse or better. That's up for debate. So we'll start with opening up a X-ray data set. Does anyone do you have a preference, Joss, on which data we start with? No? Okay. We'll go and we'll start over here. I have a lovely folder all on this. Actually, you know what? I'm going to start over here. Yeah, this is the one I'm going to start with. So this is, let's see if we can find the right one. Here we go. This is some marvelous data. So once you open a data set, you usually get something like this, where you get the data channels of the images in the data channel box there. And if you want to see how that looks, you can click on any one of the channels and you'll get an image display of that particular one. When you're opening SSRL data, in particular, oh, there, it's catching up. When we're opening SSRL data, there's always because we're doing a continuous scan, there's always one pixel on the far left side of the data that's a kind of a warm-up pixel as the detector is starting to count and the stage is getting into the area. It's usually annoying because it has a longer count time and it biases the scale. And so you can use this slider to scale down. And as soon as okay, definitely have a lag, but you can do it. It looks great up here on my screen. Well, you can believe me now that I've taken that slider down a little bit and shown a much better update. Let's see. There we go. Just like that. We'll see how well Zoom captures my screens here. And we can see much more of the sample this way now. Now, the other way to do this is, if you don't want to work with a slider, is if we right-click on the image, there is a edge removal. And that edge removal will focus one pixel, zoom in, and get rid of that bad pixel on the side. And you can scroll through the various data channels now and see all the elements that were collected. And if you like to see log scale data to bring out your lows better, you can click on that. There we go. And do various image display of your elements that way. I'm a personal fan of the default JET MATLAB color map. If you don't like JET as much as I do, there's a whole list of them. The new Viridis is kind of the new popular hot color map nowadays, right, for the kids. But so it's a more dynamic scale that doesn't bring out the highs and lows and bias your eyes as much as, say, my favorite JET does. So now here's that data set. We can also, this means there's, I'll just say briefly, there's lots of pieces in the MicroAnalysis toolkit that we won't directly talk about. But we can do things like make correlation plots to look at how different elements correlate quickly. Potassium and sulfur, maybe, for instance. You can take a look at these correlations. We can define masks to say, where is this particular correlation on the map? And once we set that mask, you can use that mask and it identifies those regions of the map that have that particular correlation, right? We can go back to ignoring that. If you don't like this lovely green on black color display, we have lots of themes. And so if you prefer to see the density of plots, because there's a lot of points in this map, and a few green dots together look like just a few green dots, you really don't see what it is. So if you go to density map, you can see that all your points are really in that lower correlation rather than the upper one. And if you draw a mask like we did, we can also go and say, use the highlight mask. And use the highlight mask, there we go. And turn off the color plots, there we go. This will now show the highlight of what part is masked. And that's great if you just draw the mask, but say if you wanted to come down and say, I wish I knew where this section of hyphae were, you can highlight a section here and mask it, and it will tell you where that is on the correlation plotter too. Now, you probably saw me draw that quick box. There's lots of little keyboard shortcuts. That was by holding Shift down. But if you forget what they are, like I do all the time, there's a little help screen here, and that will tell you all the keyboard and shortcuts. And so if you can use the Shift to hold down to draw a region, Control to zoom, and I think it's Option on my Mac, but it's Alt on the PC to draw a cross section. So there's a lot of things that you can see here, and all those shortcuts are listed in this help page. So it's a good place to go. And if I ever ask you what version you are when you report errors, you can always go to the About page. And I'm cheating because I'm actually on my new version. That's 3.0.10. So shh, don't tell anyone. It's just not released yet. The best thing, though, is also, if you do decide to use the software, there's a lovely reference about how you can actually use this in your final paper reporting. And this program wouldn't be nearly as good without other stuff that I've borrowed and used. So two big ones are XRF fitting by PyMCA and FTIR processing via octaves. And so if you do use those features, I highly recommend you cite my co-conspirators in this as well. Citing is always friendly. So let's see. So there we go. So correlations. I always like to just show that briefly. And we're doing this with X-ray data, but we can all do this now with any of our modalities of individual data. So if you're doing Raman peaks, if you're doing mass spec peaks, infrared peaks, we can correlate those intensities of those peaks, masses, vibrational frequencies, and do the same things here, correlate, see how they relate on the sample, and see where they are on the sample and where they are in a correlation plot too. We saw a lot of these kind of images yesterday where we showed three things all together, and it makes this lovely red, green, blue tricolor plot. There's a place for that, of course, too. And we can say red, green, and say blue. And you might be able to see some of that. You can also scale these quickly by typing in the max scale you'd like to see. And we can bring out those colors. Maybe a little bit cleaner there. So you can kind of see how those elements all co-correlate on a visual image now too. With all these bits and pieces that we were going through, I'm going to go back to the correlation plotter for a second. You can see that you have a data here, you have a tricolor display here. If I go in my map and I decide I wanted to look at that one region, I can zoom in with me on the control there. All those images will all snap together too now. And so if you're doing tricolors, statistics, correlation plots, they will all change based on your current view. So you can always take a look. It's always going to reflect what you're currently looking at. And you can keep on whittling down to see a few points here and see those in tricolor or correlation. And you can see that you get out of one correlation. And if I clear the zoom, clear the zoom, it all comes back. And you can also see that there's that little weird edge correlation. Go back to that. You'll see this with a lot of our XRF data. There's these pixels here, which look really strange. And that's our edge data again. So if we remove that, that part goes away. That's that one, again, bad pixel on the left side. Okay, so that's been exciting and fun. Basic features of what we can do with the tool, just for visualization and quick viewing. But now we want to put things together. That's the whole point of a lot of this, right? So when we take our data at our beamline, we have a mode where we take a mosaic image and put it all together into a big mosaic, and it overlaps about 50% of each image, so you get lots of overlapping tiles. Most of your other vendor software will probably mosaic that for you and create some sort of JPEG, hopefully, which you could just import directly. If you have an SSRL mosaic, there's two main different ways of doing this. A static mode is just going to put it all together based on the coordinates, and the machine vision will do its best job to find all those tiles and see where they all go together. They both have some degree of success and or failure. But we can take the raw image that we took for this one and open it, see if it works. It's thinking about it. It's ironic that the optical images are actually larger than our data sets normally now. because we're taking nice 5 to 8 megapixel tiles, and our data is maybe only 1,000 by 1,000 pixels. It will stitch it for us. Oh, actually, it even worked. It's even better. I also will recommend that if you are running this from your command line, it's always good to kind of watch what's going on there. When things do go wrong, usually will tell you. And then we can say, yes, I'd love to load that file. And it's probably going to be some ginormous image here. Yep, ginormous image. And you can see here it is all opened up. Quite often, if you don't have a giant 35-inch monitor in front of your desk, you won't be able to see the entire image. But you may want to see the entire image. There's 2 tricks again for that. If you just want to be able to change the color map to say grayscale, so you can kind of see how it looks in a photograph, you can just kind of do a quick zoom on one portion to get the color map selection screens on the bottom here. And we can go back up to a grayscale like that, and we can invert that to make it look the right way. But that's, again, only seeing a corner of your data at a time. The other trick is under view. Under view, we can apply a scaling factor and just shrink it by a factor of 2. And that usually is pretty good. There we go. We can take it off log scale because we don't need to log optical images. And there you can see the optical image of the sample, the hyphae on the tape. Because it is a RGB image that our cameras take, you actually do get blue, green, and red channels. So if you are trying to do some color analysis, you can actually use those red, green, and blue channels. There's a lovely grayscale as well. If you'd like to see how your data looks in living color, you can just do a tricolor plot with your channels. I'm pretty sure this is going to be very gray, so it's not going to be that dynamic. But yeah, did it actually have some color to it, though? Oh, well, let's take a look. Now you may be wondering why the tricolor image is giant and my other image shrunk. It's because I haven't written that part of the code yet. But trust me, I'm aware of that, and that will get fixed in a new version. So yeah, you can see there's a little bit of color to these little corners here, a little goldness to the hyphae there. There's how you can see your images in living color. We can save any of these images at any time. There's the file menu. And down here, we can save displays, high res, tricolor displays. There's always a scale. I'm a big proponent of when you display an image, you should probably show a scale bar, and you should probably show an intensity bar. And I am very evil when I'm a reviewer on these kind of papers when those are not present. Not that I would ever be mean to anyone in this room. But if you want to see a color map, you can go to Legend and you can say View Color Map, and there's your color map scale from 0 to whatever. And if you adjust your color scales here, oops, of course now it hides. It'll probably take 20 minutes for that to happen again. There we go. You can actually watch your color maps will scale appropriately too. If you want to make your data match someone else's data or another data set, I can always, if you want that maximums to go above the max of your data, that is the default. But if I want to say, okay, well, someone else had a color map that went to 400, I can just go to 400 here, and there we go. Now that's rescaled to 400. Of course, now we're 80% of 400, but let's put it all the way back up. You can do it. You might want to do it. You can go. If it decided it wanted to do it, it would do it. In any case. I'll just actually mention this too. I've tried to organize the menus so they make some logical sense. You may beg to differ on that sometimes. Most things have to do with file input and output or in file. Things that involve looking at how you want to see your data, looking at the correlation plots there, changing the size and those kind of things are under view. There's a new feature that you'll see in 3.0.10 that if you don't like my plotting palette of colors, sometimes they're hard to see, you can change your color palette of how things plot. There's like several choices to make it look pretty. You might imagine that process as things that you can do to process your data. So this is like image processing, changing resolutions, making corrections to your data set typically, filtering, blurring, manipulating your data, hopefully in a very normal way. Analyze will be data analysis. So these are now things that you can try to quantify and get numbers out of your data. So we have chemical imaging with Zanes fitting on top of our data, for instance, for XRF data. Lots of the PCA analysis stuff goes in here. We'll go through some of this as we go along today. Clustering is in here, averaging data, making profiles through your data, getting summaries, moments, doing statistics on your data sets, segmentation. All of this is all under the Analyze menu. You saw Legend. So in addition to showing that scale bar, we can also go to, there's a show scale bar option there as well. That should put our required scale bar on there in a second here. There we go. It always scales this to about 10% of the width of your screen. So if you want to change the number, you can kind of adjust your zoom. If you don't like where it's placed, you can say place scale bar and tell it to go. I like my scale bar right in the middle of my image, for instance. I don't, but if you did, you could put it right there in the middle. And then you realize that you probably did something wrong, and you would say that let's go back to the default, and they would put it back in the right place. In a second. There we go. Right? Pardon me. We also have what we call MCA analysis. These are all analyses that go with the full data cube of your data set. And so for XRF data, it's the full XRF spectrum that we can operate on. In Raman or infrared, it's the vibrational spectrum. In MALDI data, mass spec data, it's the mass spectrum. I kept it all as MCA. Maybe I'll make it data cube at some point, but it's all the same idea. It's all stored in a separate file so that you have a lighter weight data set that has the channels, but we can access this through the MCA menu. And we will definitely get to that shortly as well. The last thing I'm going to mention too here is that there's a new menu bar with SMAC 3 called Workflow. And you might imagine it's just that. We can actually now create workflows of all the different analysis that we might do. And this kind of gets to the idea of trying to do a standard process or a batch process. Because quite often we play around in SMAC around, we kind of see what we want to do. And maybe you took some good notes, if you're lucky, about what you did to process it. And when you write it up in a paper, you're going to want to write it up and go, I did this step, that step, right? And then you want to go to the next data file and do the exact same thing. And you probably forgot a step somewhere in there. And you get halfway through it and you're like, oh, I got to start all over again, right? So most of the steps that we're going to be talking about today are in the workflows. There's a few here that are defaults now. So, for instance, I get really annoyed by that left pixel on my data. And so I open up like 20 files and I have to go through and right click, remove, and I'm getting carpal tunnel within 5 minutes. If you go to workflow and say edge removal, it'll take all the open data sets, remove the pixels so that you can now see it. So it's a nice standard way of doing things quickly. Maybe you want to blur all your data sets to make them look a little crisper, or to increase your, look at different signal to noise ratios. So you just say blur all channels, and it'll blur all your data sets for you all at once. This again works with all open data sets, all open data files. So you can create a standard workflow and ideally process many files at once in a very parallel and the same way. If you were paying attention when I was showing you samsxrays.com, there's also in a section after installation help, there's a section for workflows. It really just has, hey, there's workflows now, please share. And that's where we are right now. So I'm hoping though, as we develop more workflows, as people come up with workflows, they decide to share them because they are exportable and importable. And this is a good idea to get the community, again, to think about how they want to process data and come up with standard ideas that are shareable. And that's, again, we all want to do the same thing to a lot of our data sets and in a very repeatable way. So having the ability to share a process is nice. It's not quite as fancy as like, if you're familiar with Orange, where you can make little graphical models and draw them all together, but it is a little list. So I want to do these steps. It follows through. Welcome to take, I don't want to program in a graphical language. That's beyond my desire and my free time. But hopefully it's handy for many people. Okay. So we've digressed nicely. So here we are with our picture, and here we are with our data. We want to put those together. Ideally, if the data was taken correctly and nicely, they should match up really well. If we look at when I scroll over the data set, you can see on the bottom right corner of the map, you get a Z value, which is your intensity at that pixel, and X and Y are the image coordinates. If your data file has data coordinates, I try to extract that. If I can't find data coordinates, it's just 1 through 1,000 or whatever else pixels. So if you open a JPEG image, there's no coordinates on them. It just looks boring numbers. But ideally, we can now merge those together and see how they look. Now, the interesting part here is the image data is actually a higher resolution than our X-ray data. How do I know this? If you don't know what the resolution of your data set is, we can go to process, and if we go to change resolution, it tells you what your resolution is. So this is saying that this optical image is at 1.1 micron resolution on the data set, on the image. And that's about what our camera does in a very nice way. If I go back to my X-ray data, that looks bright and crazy there. Let's go to something that we can see. There we go. It's much smaller because we're still shrinking it, of course. There we go. And you can see here, our high levels here are now 29,000. If I do that same thing and go to process and change resolution, you can see that this is collected at 15 microns. So we have a 1 micron data set versus a 15 micron data set, and those don't match. There's multiple ways of doing this again. The quick and I would say dirty way to do this is we can go to the image here. And again, if it's collected on the same area that we have, I can just say export within the tab and resize it and squish it to the other side of the data set. So we export with resize, we take the gray data, and we say, yep, send it over to my XRF data. And if I click over here, now I have a new channel called gray, and it's been downsized and downsampled to match my data set. And if I start looking at it, oh, it's pretty good. Let's see, nicely aligns. Beautiful. If I'm really picky about this, I could go to the tricolor section here, and I could try to see how well these actually align. And there we go. And it actually looks pretty good. You can see that there's areas in the optical image that are larger than the X-ray data, but that's okay. There's parts of it where we just had better signal than others, and there's still low signal around that. Occasionally, you will find that they don't exactly match. The reasons for that are often when we have our optical images and whatever technique we are, if it's not exactly along the same axis as your data collection, you can have a little bit of parallax. And so if you're off focus on our XRF lines, if you're off focus on your instrument at home, those may not always match up. You can do some crude measurements in the math section to say math, and I can choose a channel. And quite often I have to do maybe at worst a quick horizontal and vertical shift a few pixels left and right to match that up. Luckily right now we're doing okay. Now I showed the example yesterday where we took data from a high res map and a low res map and we fused them together. If I go back to open here, you can look at this high res data. So this is this one here, I think. Nope. Nope, it's not that one. It's this one. There we go. There we go. So this is a high-res version of that corner. Let's go back to a color map that we might enjoy better to see those dynamics. There we go. Don't need to invert it. There we go. Now, again, if we're maintain the same focus, the same levels, these coordinates should be exactly the same, and we can just import this map right on top of the other map. I can go to our data set here. Now, there's this lovely import data button. So if you want to import data from one data set into another one, you have to use the import data button. The first thing it's going to say, though, is that the data sizes don't match up. And it's going to warn you that the map you're trying to import may not be the same size. We also need to worry about resolution now, too, because these are also collected at different resolutions. So if I take our imported map here, our small map that we want to import into, I can again look at the resolution here and see that that's at 5 microns. And so what I'm going to want to do is take my course data. I'm going to want to scale that to 5 microns now rather than 15. Of course, this is under my zoom bar now. I can still get to it. We can save it. It's already been done, so I'm not going to overwrite the data that I have there right now. It will create it, and then you can open it. I'm going to open it here. This is, and it puts the note here on the edge of the file name that it's been scaled to a different resolution. Now we can see it. So this is that same data set now, taken from 15 microns to 5 microns. I can go from the file menu and I can say import from file. When you do this, this will actually now take into account the pixel positions and the sizes and match it up and import it in the right place. I used to have to kind of guess about where to put it. Now it actually looks, and smart computers are good at this, looks at the coordinate positions and tries to match it in the right place. But I got tired of it because it does ask for a lot of prompts. And so the import button, that's a tab there, is actually the rapid import, which will not handle doing manual adjustments, we'll say. So I can import this smaller data set here. Here we are at a 5 micron version of that. If you notice, the data set we had before was 5 microns as well. I often get that left pixel that I hate. Whenever you zoom in to your data set and you go through the export data set, it will export the zoomed in version that you have. If you want to take another data set, put it to a larger data set, if you don't do this quick little step, you'll still keep that left high pixel and you see a big red line on the left side of your imported data. And you may not want that because it doesn't look good. So if you resize your data to the same size that it currently is on a zoom, it'll take that into account. So I've done that here. You can open it. It warns us that it's a different size. Do you want to buffer or crop? You say, yes, I'd love to. I'm going to do this with the potassium data. You need to tell it what it is. This is from the A sample. I'm going to give it a little bit more information there. And it's now telling us that if I want to take this smaller data set, it reads the coordinates and it tells you that you need to put in 600 pixels to the top, 158 at the bottom, and pad to the left and right. You can adjust that if you don't like those numbers, but usually they're a pretty good start, pretty good guess. And if I look down to the bottom here now, oops, this data set, here we go. And there's our small little mini fungal area. So now I've imported that into my larger data set. That's great. Looks like it's almost the right place. And if now I want to merge these two together, if I just do a addition, it's going to use both images, and that's going to not be very nice. And so I can go and I'm going to process. I'm going to use this current channel that I have, and I'm going to create a mask. Let's see, where is that? From the channel. No, no. I know it's here somewhere. Use current channel as a mask. So anywhere that there's data that's not 0, it'll make a mask of that. There we go. So if I use the mask, that's what it looks like. I'm going to replace the data that's over here in my other data set. So that's the mask, right? I can take my large data set here, and there's my mask. And I'm going to say, I'm going to go to the process, and I'm going to remove the mask from my channel. Now that's zeroed out. Now I have a lovely hole in my data set. And now I can use map math and add the calcium, potassium, I can't read my elements today, and add those two together. And this is my new K fun, something, right? We'll call it K merge. And we'll save it. And there we go. There's our high resolution inset into our course context data. So this is simple because this is now same beamline, same sample, different resolutions. We can do this with different beamlines across SSRL. And now we're going to try to do this with multiple modes of other data sets now. So this is where the fun part will come in, right? Any questions on anything that's been so far?
So if you have, maybe if I took a map of the entire sample, I'm asking about this like last thing that you showed here. In like the 7.2, the large format beamline, and then I take that sample to maybe 14.3, and then get like more fine resolution. Then I can put I can do the same things, showing, okay, this is my, bigger data, which is coarse resolution. But then, okay, here is like certain places I want to highlight.
Definitely. So that's another great way of doing your contextual data. And you can even say, here's my data set at 7.2, it's coarse and big scale. But I really want to now really show you this high res little area in the section here that I got at a different beamline at a much higher resolution that it's capable of doing. The only difference there is the coordinates are going to be different between the two beamlines, right? So we have one case where we have our small, like 1 centimeter stage, and then case where we have the meter long stage. So they're not going to match coordinates. So this is where we treat it like a separate mode of data, and we treat it like MALDI data or IR data, and we use those visible images to those together. I think I'll actually go and do that in a second here too.
Is it possible to record your steps, so create your own recipe or workflow?
I don't have a capture, step capture yet. It's been a really good idea. I've liked that idea for a bit. I haven't implemented it yet, so it's on that list of things that would be nice to have. May not come out right away in the next version, but it will probably come out in the future.
And a different one, because you talked about the scale bars in the beginning. Is there a way to change the size, font size, or add micrometer?
Yeah, so it does it in whatever the units of your data are, right? And so all of my X-ray data are in microns, and so it scales it in 10% of the view. So it's usually a nice, normal, not too in your face section, right? And it rounds it up to the nearest 100 or tens that makes sense. It tries to only give one significant digit. So you're not going to find a scale bar F like 405 microns. It'll round up or down. And it'll do the closest thing to 10%. I have not made it flexible, so you couldn't just say I want to see a 1 micron scale bar on this data. But it's an option that we could support if you wanted to set a precise value.
Font size?
Again, it's also the default view here. So often what I do often is export it with this, and then I'll come in with a text bubble and make it bigger for a publication if it's too small. We have a question 2 rows back there.
Okay, what exactly happened on the big map when you said like change resolution? What is actually happening? Like it was 15, we're not magically increasing the resolution
no,
of the
no.
course map. So like what is happening?
Oh,
What
yeah.
is SMAC doing?
Yeah. So if I look here at the data, right? I mean, it's a big file here right now. And so when I exported it to 5-micron resolution, it does a bicubic sampling and it turns 1 pixel into 25 pixels, right? That all have roughly the same intensity. So if we zoom into the map here, right, you're going to see that the pixels are bigger and they're being resampled, right?
Okay.
And so it actually does a bicubic sampling, so it kind of smooths through it a little bit, so it's not just big blocks. And it's kind of like the idea of like it's basically blurring the data on a 5-micron grid, effectively, this bicubic sampling.
Yeah.
You're not magically gaining resolution, but it's putting it onto a better scale.
Okay.
Right.
Yeah, that makes sense. I also just want.
And the same thing if you can also go from 1 micron. When I went from 1 micron to 15 microns of the optical image, it's downsampling that in a bicubic way too.
I also wanted to say that we have, for all of the SMAC basics, there is a lot on Sam's website. So like if this is all new to you, even some of these basic things are on the website. We also have YouTube videos. They're a little old, but the base processes we still use them. They still matter.
Yep.
They still work in the new SMAC. And so highly recommend, if you don't know what you're doing, to watch those videos. They're really helpful.
That's a very good point.
Yeah.
There we go. We have a confirmation here. They are very helpful. See,
yeah, we made them for a summer school during COVID, and they have been very helpful for us to ask users to maybe watch them before coming to the Beamline. There is not new SMAC documentation
yet.
We're working on it because Sam has to also tell us in the group how to do these things. So I have some notes on some of these things. I also have how you can install a desktop icon to run it from your desktop. I have that. So we have some of this. It's just not like out. And so if you do want some of these notes, then I can also share those with you.
This is the problem that we're getting at right now, is that we're
Yeah.
developing faster than I can document, which is a fun thing for me because I thought, oh, this is really cool. And like people, even Jocelyn and people in my group, like, oh, I wish I could do that. Oh, I did that a month ago. And they're like, what? So it is going faster than even I can document. We're trying to catch up this summertime. So hopefully you'll see some more documentation coming out. I will also say that if you've figured things out, or if I've taught you, there we go. Desktop options are very popular too. It's not on the forum yet, but that's a good place to put it though. Haha. Yeah, so documentation is coming forthwith. And yeah, so if you do take notes to this, or you come back and you rewatch this video and you want to type something up and you think it's useful, your notes are really good and are good teaching things, you can email it to me, and you can be credited in my documentation as like, this person took awesome notes for me. Thank you. I'm not above soliciting help to write that documentation. The more people that help, the faster it'll get out there. And I don't know the exact YouTube address, but if you do Google SSRL Summer School YouTube, it'll come up pretty quickly, and you can like and subscribe if you like, so. Any other pieces here? Okay, excellent. So let's get to some actual merging of data here before my time runs out. So we are going to start with something else. So like occasionally I like to say, that's been really great, but let's start all over again. So I'm going to close all the files. It does warn you that maybe you made some changes. Maybe you don't want to close it right away. It often says that even if you have saved it. So it's always a good reminder, like, did I save that data file? And you can say yes or no. There we go. So we are going to move over. We'll go to the stem here. So this is going to be infrared data that will merge into our XRF data. So this will be fun. Okay. So We have our data here. And this is data at 7.2. So 7.2, this is our large format beamline, same fairly small sample, but still taken at, let's say it was taken at 20 micron resolution, roughly. And then we also have a data set here where we have it here at 3700. And potassium, I can, oops. See it here at higher resolution, and it looks much better now since we're now at the much lower to the potassium edge and being very close to that edge, and we can see the data much better, much more contrast in the potassium. Now, this goes to your question, Arunima. So here's data on from 2 different beamlines, different resolutions, and different scales on it, right? So we have to do the merge my data type of method here. So the first thing we're going to do is I'm going to look at this potassium data. I'm going to look at it, and this is at 6 microns. And I'm going to say that I'd rather see my data at 6 microns than 20 microns. I'm going to go for the best resolution I can. So first thing I would need to do would be to take my 7.2 data and change the resolution. Whenever we do these, it's a nice thing to have the same resolution. It's going to be a much easier step. And so I would say, go to 6. And did I already do this? I bet I did, though. So I know I did this for my talk yesterday. Well, maybe I didn't. Okay, we'll save it. There we go. There we go. Here we are at 6 micron resolution. And now these, lo and behold, they actually look to be similar sizes because they're the same resolution in the same sample. Now, again, we can't just import it over because we have different scales, different coordinate systems, or similar scales, but different coordinate systems. But we do have optical images. So we can use the optical images to try to correlate. Did we have, let's see what we have here. I'm going to see what I've opened. One thing we'll notice is when we open up that mosaic, it does create a image out. So you don't have to constantly convert those mosaics back into data sets all the time. So here we are. Here we are. This is going to be 7.2, I think. Oh yeah. Well, that's 14.3. And then we have eyesight's going. Let's see if that's it. Yeah, and there we are at 7. So we have optical images for both of those as well. And so what I'm going to do is put these images in their respective data sets. So this is the 7.2 image. And this is where we see, or 14.3 image. This is where we see that right now, at this exact day, we have different resolution cameras on the 2 different beamlines right now. Old crappy CCD camera and a really fancy new high-res camera. So that's why this part of this data looks really awesome and the other one looks not so awesome. When I get back on Friday to SSRL, I'm going to put the new high mag camera on all the beamlines, and so this will be less of a annoying issue. But it's a good example to say different camera resolutions, different CCD resolutions, how well or not well things work. So we will export the resize in the grayscale channel, and we'll shoot this over to our 14.3 data. That's it, yep. And we'll take this over here, and we'll export with resize and shoot the gray channel. Now, some data sets, so again, with SSRL, we save our mosaic in a separate data file. I have not seen many data formats from other people, from other beamlines or other places that have the optical image embedded in the data set perfectly. That's just an unfortunate matter of fact. So we have to do this little step to import the data over. Now, I will say the Renishaw Raman does store it, the optical image right nicely in the data file, and that gets imported right in all at once. So you don't have to worry about this extra step. So if you do like to use Renishaw's, that is a bonus. So now hopefully we see here, we'll have our data set, and there's a gray channel, and it looks pretty similar. Did I do the wrong one? No, I don't think I did. Yeah. So this is a case where I'm gonna look at the other one too. That one looks much better. If, for instance, you took the image at a different focal plane, it might not mesh together. So I'm pretty sure that the 7.2 image here was taken not exactly in the same scan area as the data. Because when I put it together, they're in different areas. You can see this little blue part over here. It doesn't have the same aspect ratio, even without sampling. So I could do some things and zoom around and do it, but I can also use this method of coercing these data sets together too. And so we're going to find that coercing the data is going to be a popular theme often, because when those, remember from the talk yesterday, when you try to put the data sets together and they all look like you're going through a time warp, when the merging doesn't work, we have to do the manual steps. How do I do the manual steps? So we're going to have to do that with this data set here. Quite often we have interface called the plot marker area, where if you've taken spectra at locations, we save all those coordinates, and you can put your XAS points over your image data and make it and see exactly where you took all your data sets. And you can make them look all kinds of pretty colors. Luckily, I have gone through this process recently. So I believe it's going to be this one, 7.2. And here we go with a whole bunch of markers. And so you can see you can get numbers on them. It's great for your showing your publications later on. You have lots of options. Text, you can make it whatever you'd like to say. You can also make them all kinds of different colors, different shapes. And if I'm too lazy to check all those boxes, I can say make them all default, goes to points. That's easier for me to see. You can switch back and say set all text. And when you do that, it actually does number it 1 through n. So again, you don't have to count. I'm pretty bad at that too. We'll go back to default. So here we are with those markers on that. And if you notice, what I've done is I've picked markers that define the shape of the sample here. This method does work fairly well, unfortunately, when you can't make the images merge well. But it can be a pain, and I'm trying to do it better so that you can just kind of draw a shape on there and actually get hundreds of markers rather than just 10. It gets really annoying to try to match exactly 30 markers from 2 different images to be precise about it. So that will be a new feature that you'll see by the time you get the next version. So here we are with this one. Again, I think NPM, yeah, I want to say it's this one. It's not that one. If they don't show up on the screen, then you know it's the wrong one. This is, that's 14.3, okay. Where is it? We'll tell you what, we're going to cheat. Now look at this one. This one was better. I'm going to open. So work with this one. that's what I did. No, that wasn't a very good idea. Here we are with a 7.2 data though onto an image, and it does match up. I'll go through that process with the two data sets rather than that image. Here we are with this one. There we go. We have plot markers for both of these. We can try it with the image. Have a gray here. Yeah, this will be a good example of how things don't work, because I'm not above to show when things don't work. So whenever we want to merge these data sets, there's the export with channel registration concept here. And so this is how we do all of our multimodal fusions. I'm going to take, for instance, the data here from 7.2, and I'm going to shove it into the high resolution map of 14.3. I'm going to use the grayscale image from both of those data sets together. And I'm going to ideally export maybe my image and the potassium channel. There's a whole bunch of methods on the bottom here. If you were seeing Peter's talk yesterday, you might recognize things like the orb and the sift. These are image registration methods, and they're very resolution specific and image specific. So, but when you do have nice images that do work well, it does work, and you can just say do registration here. And here it shows the points that it thinks are similar on both maps. And so it's drawing correlations, and it finds lots of great matches. And there's your space warp. And so here it is, it's merged it together. And you can definitely see that those two images do not overlay well because they are very different. And there's your transform. That did not work well at all. And particularly, and when you look in the bottom of your window here, you can see there's a shear value of 6,000%. That's pretty high. That's why it's all, it's time warp, space warp kind of thing. And it warns you like, yeah, that's a little abnormal. How about you cancel? And you could say yes, but I recommend that you don't. And you start over again. And so you might say, okay, well, maybe that wasn't the right method. Let me try the sift method. It looks a little bit better. It's still time warps it. It's not as apparent. Okay, fine, that's still abnormal. And so this is now when we're going to go to the manual method, unfortunately. It has different ways. So the percentage takes the top 0.5% of the matches because it finds a ton of bad matches as well. The KNN does another way of sorting out the matches, looking for the nearest neighbor matches. Usually just makes lower percentages. You can just try it one time to see if it works any better. I'm pretty much going to say it's going to be no. Yeah, so here it does. It really did a really good job of removing all those bad matches, but now they all match on the same to one point. And it's going to say at the bottom here, matrix failure, because it only had 4 or 5 points, and you actually can't solve the transformation matrix with only 4 or 5 points. So it did a much more aggressive removal than we would have liked. But now we can take a look at, this is 7.2. I did go through this arduous step earlier this week and found our 7 points there. I think I did it with 9 points here. And I can come to our data here, and we can even look at this marker list here. And you can see that I've picked out the same 9 points there pretty much. The better you are at picking out the same features, the better the transformation is going to be, the manual move. So it's nicer to pick things that you can find again, obviously, right? But now we just say we want to go to manual data, and we're going to use that exported marker list. So it's an easy way to take things in SMAC, use one set of source points from the 7.2 data, and merge that into source points, destination points in my 14.3 data. And now I'm going to say do registration again. And it's much better, but it's on a flip. It's like there's always something, right, that's going to stop you, right? So in this case, now I can actually take my data and flip it around and make it work. It does work. But these are the kind of things that you will get to when you try to register your data. These are common problems that we always run into incessantly, unfortunately. But it did look pretty nice. It still says it likes this one better. I'm still going to say no. So what am I going to do to fix this real quick? Well, I'm going to, again, do this really quickly and just flip my data set around. Luckily, I've done this, but there's multiple ways of flipping your data around. If you want to keep your coordinates intact, you can do file transformation and vertically flip your file. I'm going to do that. Yes. And up until yesterday, there was an error in this process. I fixed that, so now it will really work well, I hope. There we go. Sure, load the new file. There we go. I'm going to restart this process. So now we're going to go taking this data into this data, I'm still going to use my gray scales to compare. And when I finish, I'm going to export these channels. I'm going to say export them all because we're crazy that way. We'll again do this manually with 7.2 into 14.3. And it still did it. Okay. Just when you think you had it, it doesn't work, right? So we're going to do it one more thing. See, it's great when we show things that don't work. This is what's going to happen on most of your data, right? No, it is perfect. Don't worry. Don't worry. Let's see. Oh yeah. You can tell that when I've run into problems repeatedly, they turn to a menu option. They happen to make them go faster. So there's, hey, perform vertical flips. Look, this has happened before. Trust me. And I'm just going to flip all this data over. There we go. Vertically flipped data. And now, of course, it's not going to. Well, maybe it will recognize it here. Let's see. Oh, it did. Oh, look at that. That's great. I'm going to take the vertically flipped data. Oh, it's still looking at the grayscale though. So let's look at this one here. Oops. Nope. I didn't flip the image. So let me do that. Now it's good. Yeah, see, now it matches. We say yes. And now we've gone through. The one thing you see, it's going through a whole bunch of numbers on the left here. And this is actually a really important step. I can force that data from one map into another one, but now the images look great, but I've lost the registration of all my other data sets. So particularly if I have a spectra, an MCA data, a mass to charge, or a infrared spectrum, escaping me for a minute there. You still want to be able to show those raw spectrum, not just the bin data, right? And so what we've got now is in this new file. Don't look at that. All our new data sets. And so here's, silicon and potassium in our new data set, the grayscale image that we imported in there. And this is the really important part. This is the matrix index, right? And so this maps the coordinate system for all the other full spectral data from one data set into the other one now. And so now, if I did want to import MCA data, mass data, infrared data, I would tell it to use the alternate coordinate system. I'd point it to that data channel. And now when I say to look at my data at that point, it'll go and use the right coordinate system that's been mapped onto my new sample. And this looks really nice because it's nice, a flat screen. When we do this step with more complex data sets. So if you remember, yesterday we showed this exact same data set, And I showed how nice it finally mapped the infrared data on there. And let's see, I think maybe it's over here. Yep, here we go. Because that data set had been water treated and moved around a little bit, they really needed a little extra work. And so you can see that the data indexes warped and shifted, right? And so don't be surprised if you do see things that get warped and shifted, because particularly if you've done a lot of treatment to your sample and had to move it around, you're going to get that kind of look to it. So here's the optical image, looks good. Transfer, here's the infrared movement onto that. Now, infrared one, I'm going to say was a little bit trickier because I didn't have an optical image to work with. So I had to use infrared corners. I used the same corners of those data points together to do that fusion. It did finally work. But we can see that, there's our infrared data, and it's got that little warp profile to it. But we are matching our profiles the best we can right now with that. So I'm going to save a little bit of time and say, like, we did those same steps that I just did with manual on the infrared data and pulled it in. Okay. When we go to the infrared data, I will open that data set directly for just 1 second to show you how easy it is to do. Like, don't go backwards repeatedly. So here's our ALS data. So when we opening these raw data sets, if I open up the header, so in this case for the data set, I open up the header, it'll open up the large data set in the back, and it creates an FTIR data file for me. So that's what I tend to do with everyone else's formats is I don't like to, I'll support reading them, but I'm not going to support writing everyone's format. That's just way beyond my capacity and desire to want to do. But I'll put everything in the formats that I like to handle. Sorry. What's going to happen? But it will open it up. And so this is a smaller one. Pops it open and gives you a total FTIR. But now we've created a file in the back here now that has the FTIR data here for that particular one. The header is here for that one. There's the fine root. I think it's this one. Got to tell it to look for all files. The other thing it will do is that process to decode that, it's the corner again. The process to find that and extract that data takes a few seconds. But if it sees that it already has the raw FTIR, it won't overcreate it again. So one of these is going to be the right one. It must be this one. Yeah, there we go. This was even more fun if you can think about it, because this was collected in a vertical orientation and all of our data was horizontal. So now you can imagine that these things, you can try to get the image registration to take care of those rotations. I find that they don't like rotations. A few degrees is fine. But that's where we have rotating and vertical flipping. So you can always change your system. It moves the coordinates around just fine. And though we can take a look though here still, if when I go to define the file, I can grab the infrared here that it correlates to. And if I say view MCA, I can click. Whenever I double click on a spot, it always gives me the horizontal and vertical profile, and those green lines there, you may see them pop up, and it comes up with the spectrum from that point. So I can click in the backgrounds and see the backgrounds. I can come over here and look at those more proteinaceous areas. I can go around and look at all the data set around there and see the different peaks. This is also now looking at it in bin. That's my default. That's not very useful. It doesn't have any real information. Luckily, almost everyone's files has that information. And so if I go and say, look at this in a spectrum way, if I want to cancel to accept the values in the file, now this shifts to wave number. And so now you can, this is the same thing you do with now mass spec data. You do the same thing, change to spectrum, and it will change it into mass to charge versus into the wave number. And we can do things like rebinning data. This is going to rebin it with bins. I can use the value axis, that spectrum axis using wave numbers. If I'm really lazy, I can say bin every 20 wave numbers through the whole data set and give me not specific bins, but a rough bin of all my data. And I did this with both the infrared and the mass spec data yesterday just to get a rough channel so I don't just see a big top channel and I can see the different bits. And that's how I made that animated movie yesterday, was just by binning through every half mass to charge over a range and then animated a GIF with all those images. That's going to become a file option soon to say, like, make me a cool looking GIF for my data, for my presentation. That's going to be in the next version. What do we want to say? So then if you do have X-ray data, you can interface with PyMCA here. Oops, big, small, okay. It's one thing to be able to see the data, but you may want to look at 2 different points. And so you can go and load different buffers up and compare different sections and do this with multiple things. So you can overlay those data. This is not the background subtracted data. I'm not going to go through that whole process, but it's safe to say that when you do background subtract your data, you get a new file that has IR corrected. And now if I double click on these places here, I will get my background subtracted data now instead. That's a high point. There we go. So I can now go through the other ones and redo it. This is the section where we can do those types of things, doing the background and corrections. We also had data sets that came in both reflection mode and some that came in transmission mode. So if you want to convert your functions back and forth, so you have positive peaks versus negative peaks, there's a conversion for that too. Now, I'm going to go back to this data set here, this one here, no, this one here. So this has our merge of data. We do now different processes to this. I can take these data and compare them. And again, remember yesterday, if I look at this data here in the Z, so this is in units around 100, and my XRF data are in units of, for instance, edge remove again, 34,000, right? So if I try to do any kind of comparison or analysis of these data sets together, they're going to be vastly different scales. So this is what I was mentioning yesterday is, we could go right into PCA analysis. We have lots of different versions here. Pardon me. And you can do things like PCA, factor analysis, non-negative matrix factorization, all the things we talked about yesterday, k-means clustering, Gaussian clusters. If you go to the scikit learning page, it'll show you what all those different ones mean. They are basically for different topologies of your data. Most of the time, a lot of those, while they sound cool and fancy, they are all these different algorithms for doing clustering. They work really well on really tiny data sets, not really good for large data sets. So things like k-means and Gaussian are typically the best way to go about your data. But now I need to actually tell the program how we want to weight these areas differently. So if I go to analyze, I can go to group weighted PCA analysis. And so I'm going to create 2 groups. So here's my data set, and I'm going to say, take my X-ray data. Just 1 second here. I got a cough again. I don't want to blow out everyone at home. Yeah, there we go. And I'm going to take my infrared data that's been binned appropriately. And I'm going to do the factor analysis here. So again, this is now using the covariance matrix rather than the variance matrix. And I can preview that. And the potassium is weighted so much higher than everyone else, it blows out everything else, right? And so that's clearly not the way you might want to do it. But I can even say, well, weight this a little stronger and preview again. Now you can see how they weighted that data differently. It's got more weight to it. And there's even a little bit in the DOS window here that tells us, or the terminal window. See, I'm old, I call things DOS all the time, right? And you see how the group weighted. So it looks at all the eigenvectors from the analysis and gives an idea of what the total magnitude is. I started doing this and I kept on like moving the slider bars up and down a little bit and trying to get them to match. But if you're lazier like me now, you can say auto balance and it'll go through and do a couple iterations and balance it so that they're weighted evenly now. So that's a quick way to do it. And of course, the potassium data is really intense, so it does bias it a lot. But you can see now the sum of all the infrared data, though, is similar to the sum of magnitude of all the other data. Now, it is because the potassium is so incredibly strong, I could repeat that and remove the potassium and say, potassium's there. I don't care about it so much in my analysis. And now I could do that balance and see that now all those channels, because you don't have one XRF channel that biases the data so much that it does balance out with all my other infrared data. And again, you know, with any set of fused data, whether it be mass spec, Raman, or infrared. I could save these channels now. And then what that does is creates all of these factors here. This is now showing factor analysis with the different channels that are covariant factors. I'm actually going to create new ones here for us. Maybe that it definitely is potassium. Yeah. Let's create new ones. So you go through and do this quite often. You may realize that you created a channel that you don't want anymore. And you can go down to remove channels. You can get rid of all that old data that I made when I was doing this initially. And now we can do it again and say, save the PCA. And now we have all our new channels here. Notice you can also add more than two groups. And so our goal here would be to eventually get the mass spec data and the infrared and the XRF all together. And then we would just add another group and then weight all three of those independently from each other. Or visual data, or you can keep on adding modalities to your data sets and again, treat them all together. But now we might want to see how these covary. And I recently got to the point where I realized that if I do anything else, I may lose that PCA result. And I hate when that happens because I don't want to redo all the analysis constantly. So you can save and load your PCA results. I highly recommend if you're doing this kind of multimodal data that you want to save that result and you can load it to come back to it and you want to look at it in a week or two rather than having to perform all the analysis over again. Because now I want to go into these vectors and take a look at how these vectors correlate to each other. So I can take, say, component 1 and component 2. That's this component and that component. And I can see which one of my data sets relate to those factors that it created. And so does the sulfur channel, how does that plot? How does that compare to the cellulose? How does that compare to the protein? And you can see how the vector makeup changes and how they correlate or don't correlate to each other. And this is that factor analysis I was showing yesterday in my talk. And so you can try to see how now different modes of data correlate or don't correlate, how they represent different parts of the same image or not. Now we did notice that, you know, when we did this yesterday, that in some cases, and then you can go through the different components and see how different components change. And we had it here that the X-ray data was on one axis down here, and I had two different axes of infrared data. We didn't get the awesome result like I had with the calcium carbonates and the infrared, that the infrared stretch of carbonate totally matched the calcium. But this is a much more, I'd say, more complex sample, and those infrared red bands don't actually match up with an exact potassium element or a sulfur element. And we might not expect that in this case, whereas in a carbonate system, that was a slam dunk. But now it's how we can explore now these interrelationships of the data set in a statistical type of way. I'm getting dramatically close to the end of this 2 hours. It's flown by and everyone's still awake. So I think I'll stop and ask for questions to see if we have any other questions to satisfy everyone. Hopefully this has given you a little flavor of how to mold those data together. It's a start. It's a good process, I think, and it's a thing that we're going to constantly be developing on. And so as we get more modes of data, these processes will get refined and get cleaner and easier to do. Do we have a microphone?
So that's just a feeling question, maybe. Do you think that if we collected this data on the same scale, the correlations would be better?
You know,
We could have, but we didn't. Why?
It could have, yeah.
A variety of reasons.
We had a few things that made this a challenging data set, which is why it's a really good, actually a really good example to show the biggest challenges that we're running across with multimodal data sets. We may have had a little bit better, I would say, in the core maybe, where we see things. Now, also mind you, this is just, I'm doing this with the 5 channels that we annotated really easily, right? Not with the full spectrum data. So that's another aspect maybe why we don't see a clear correlation in there. Another aspect is the, complete moving around of the sample between the different modes of data that we collected, right? The warping definitely helps that to accommodate that, but it's not perfect, right? The infrared was beautiful because all the hyphae were fresh. The X-ray data, the hyphae had kind of collapsed and not, so they kind of like all were squished together. And so we're losing a lot of that really cool halo that's really awesome in the hyphae. We're losing that in the XRF data. I would have really loved to see how that correlated better out there. So I think those kind of things are part of the reason why this is happening. But again, it does show the incredible difficulty of multimodal data sets, and when you can get them to work, what you can see and what you can't interpret them to, right? So it's not as great for seeing everything in clear daylight. Like a messiah, like, oh, everything worked great. There's all these great correlations, but it's a good way to see, okay, I can at least see how these things do correlate a little bit, and presents, again, what are our challenges for even getting good data. So
I wanted to just like add a comment, maybe why someone would be thinking, why didn't you just take the brachipodium stem back and keep it in the same orientation? And so this is how our all of our techniques also have their own subtle nuances about we simply map faster in the horizontal direction. So I took the stem and put what would make sense for our beamline, because I had a lot of these samples to get through and I wanted to make sure Sam had lots of nice data to share. And so I decided to rotate because I was thinking we will rotate the data in SMAC.
Yeah, it worked fine.
Yeah, it did. So just like, so these things, like, while we're thinking about all of these types of like multimodal analyses and like how we move sample from one place to another and being, really thoughtful and mindful about sample prep and what we're doing, there are then other things that arise related to the actual analysis of your experiment, especially when you have these advanced imaging tools where you might not have very much time, but you have many samples to get through.
Yeah. I think that actually is a good point, though, too, is, these were demo stuff that we did to try to see if we could get some good data to show in this workshop to show how we can do this. And I think it really does show the importance of if you really want to do this for a really good experiment, we need to think just like an extra 10 minutes of like, okay, how exactly am I going to get this from point A to point B and make sure that we don't have the sample artifacts, right? And so there's, and this is a really great lesson learned in a lot of ways. And this is a nice proof of like what worked well and what we want to improve on. And this really shows we need to think a little bit clearer about sample transfers, sample preparation, orientations. And you might go, if we're going to do this again in a real sample and really make these correlations, like, yeah, we can go vertical on the sample and take the extra time, right? And spend the time to take the data correctly or more adequately to be able to match that up better. So there's, things that we've learned now just in this test data set that are actually going to help hopefully everyone, like, don't keep your samples close, that orientation, keep your hyphae fresh. And the things, these are actually things that, if you don't think about all the time right away, you're going to be bound to run up against those. And now we've run into it for the workshop, and then we can tell everyone, be careful about it, right? And I'm sure we'll figure out something else that we could do better on the next iteration and the next one and the next one. And that publication is going to be awesome when it's done, though.
Okay, this really plays into my question really nicely. Thank you for setting it up. So one of the things that when I'm looking at this, there's a lot of power behind being able to take something from like the beamline and then analyze it maybe by like SIMS where you can get isotopic information,
Yeah.
overlaying that. Now, besides obviously maybe having something like fiducial marks to identify the locations or being really careful about sample prep, there's other things that we need to think about, especially if we're trying to match those very different data sets for this. And is there tool suggestions, tips that, might help make that process easier?
Yeah. And this is actually, so I mean, this boils down to like, my root idea is that bright field optical image is a really key thing. So you really want a really good bright field image that represents the data as it was collected in the exact same region that you collected. So you can easily see how your data relates to the bright field and how bright field of method A relates to method B. And in a perfect world, those images work well together. In an imperfect world, you draw your features and force the manual match. Now it's challenging when we have rad samples that we have like 50,000 layers of Kapton on it and everything looks bubbly and the optical images are horrible, right? So that's a new challenge to represent, like we don't have that great bright field image, right? This has been critical for the infrared matching because the infrared sees that's the whole reason why we do infrared is because we see totally different features, right? Those hyphae are gorgeous, right? All the organic compounds in that, right? In XRF, it looks like it's a little bit of potassium, a little bit of sulfur in there, maybe, right? So there's a vast chemical difference in the image as a whole. And so you really want that good bright field to make those matches, because trying to do a fiducial marker on all these cool organics versus metal content is not an easy thing to make. I mean, and again, that's the power of merging those tools together, but you don't have you're not seeing the same thing. So you really need a good fiducial or a good co-registration.
Yeah, just to add that a little bit, I don't know. I think our bright fields also, the confocals are quite different between so I'm not really sure if we will be able to fully take advantage. So what we did in one of the images also, Sam showed like when the hyphae, not with the root, but like, just the fungi, we simply, just use the fluorescent microscope to see if we were getting the area that Jocelyn and Sam was interested to analyze. And some of these things have like simply autofluorescence, right? So we didn't have to treat the sample. We just really took an image to guide us so that we could, just actually like guide ourselves before we go to the infrared, that we actually do get what they were sending us to, like the images somehow matching for the just certain depositions, so that we could it's a great point. I think we really need to think a little bit more about like how internally we can make sure before we go into the measurements that we could use other microscopy that within the system that, just like sort of keep us in the same road.
Yeah.
So that's a great point.
Yeah, and to go to that too, it's like, so someone says, oh, I measured this with my confocal. I did this in fluorescence, and I did this in bright field. And so like, these are all great microscopy techniques to help our finest areas, but like, what if I don't have that same technique, right? But, I'm trying to do better as our beamlines, so we're getting fluorescent LED excitation, so I have like 8-channel excitation on all the beamlines. And so we can go through and get into the UV and put the filters in to see the fluorescence, so I can match out your data better, right? And so this is the thing of thinking, we need to get our tools to match so that we can see the right things to correlate with. And with the MALDI, it was even more difficult because we had this big micro model that we could see, and then when the MALDI was done, they drew a little marker on it, and so I got the JPEG of the marker spot to the MALDI data. That actually worked out really well because the marker mass spec was different than the rest of the mass specs. I could actually see the outline of the marker and match that on the optical image really nicely. But one of the things that really helped, because part of our data was only one corner of the micro model versus the whole end of it, but I had the optical image had the whole end on it, and I could see the writing of the 300 micron pores on the MALDI in one section, as well as my XRF data. So rather than correlating optical images, I was correlating one channel of the MALDI with one channel of the silicon etched in there, and that actually worked out really well. And so it's like trying to stretch what you can match, but there's things in the data sets you have to find, and you explore the data sets independently and see where can I find the same registers when you don't have all the supporting data.
So then in terms of like just sample prep workflow, is it then easier, I guess, to have some of these markers, like the 300 micron, that writing, for example, it was not intentional, but it was there.
It was very helpful.
Okay.
And I would even hazard that, we just a little bit yesterday during the fiducial parts, but like, it's amazing how good a Sharpie can be sometimes. Honestly, it's actually a really nice, it's an easy one. Everyone's got a Sharpie in their lab. It has a great iron signal and a very unique MALDI signal. It was actually like, wow, that's actually really helpful. And some people even circle their whole sample, like that sample you can't even see with the naked eye, and they're like, go here, and they draw a circle on it. It's like, oh, that helps. So it's amazing how even the low-tech solutions can be really good. Mosh.
Yeah, this is great, Sam. For clustering, I think you talked about K-means and Gaussian.
Yeah.
Does one work better for most of the data sets you work with, and why? Yes.
Yes. No, I know I hear whenever I see K-means, I go like, K-means is very straightforward, easy to do. It's quick, it's great, but it's a completely geometric analysis. It looks at all your multidimensional space and splits it up evenly as possible. For better or worse, that's what it does. And so if you actually look at, we have like a few minutes to go.
Yeah.
No one's going to kill me if I keep on going another minute or two.
Until 10:30.
Oh, well, in that case, this can actually be an interesting example. I'm just going to start. Oh, I think I can go right to here. I'm just going to cluster some of the XRF data for ease of looking at it. So here we are with several bits. Oh, shit, I'm going to go to the nicer one. Sorry. Well, slightly better resolution. Nope. There we go. So if I do clustering, I can go to PCA clusters here, and I can. Nope, I don't want that one either. I'm sorry. That one. This one. That's the one I want. So we'll do PCA, and we'll cluster. I'm going to get rid of the potassium again since it is so dominant. And we'll go to K-means, and we'll do 4 clusters. So, and if I go to a correlation plot, we can do maybe phosphorus and sulfur. Phosphorus and sulfur here. And this is actually kind of cool. This is why I want to show you this. If we go down to the K-means clusters, and that's how it clustered out that data, right? And, spatially, it looks pretty cool. I can be highlighting this channel in the viewer, and now I can say under color, cluster plot it. And that shows you where those clusters are, right? And you can see how the k-means is very straight line, and it's really just kind of doing concentration more than anything else, right? So this is why I don't like k-means for the most part. So it's a little bit too regimented in a way. If you do a Gaussian cluster analysis, oops, that's not under math, that's under PCA. I do the same channels. I do Gaussian with the same 4 clusters. The Gaussian is doing it more of a balanced rather than a straight definition of 100 points here, 100 points there. It's actually fitting a Gaussian distribution around those 4 clusters. I use k-means to seed the Gaussian, right? So I do a k-means first and I seed it with that, and it goes through that process. And it may not be entirely different, but that's a much different cluster, right? And if I look at my plot here, it's not geometric at all, right? And so whatever space it, then I'm just showing phosphorus and sulfur, but it's weighting those other channels a little bit nicer in that sense, right? And you could say maybe it was picking up magnesium, but see, it's picking up clusters of a higher dimension than I can see in 2 dimensions. And I find this to be much more meaningful than k-means. It really biases things on the highest concentrations of stuff. So personally, that's why I love Gaussian, and I tend to disapprove of k-means.
Thanks.
But anyway, it's really powerful to see this in here, right? To see how it distributes it, right? And what's really fun then, I'll just mention this because it would take too long to do it in real life here, but now I can take those clusters, and if I could cluster on my sulfur and XRF data. And then I have my matrix transformation to show me where my mass spec data is, right? I can now say, we click on different points, right, to look at that data. But if I have my merge data file and I have that, I can go to get MCAs from cluster maps. Now it's going to average all the things that are in that one cluster and give you the average of that mass to charge spectra, or the MCA spectra, or the infrared, or whatever your modality is. And I can look at the average in a cluster of that characteristic, of whatever my data cube is. And so you can really say, oh, all of this data that's clustered by infrared or sulfur or phosphorus, what is the MALDI in that, or what is the infrared in that? And so you can actually then filter out by clusters, and it'll make those clusters in the same color formats that your cluster map is. Again, how can we do these correlations, do clustering, and look at then what does the raw data look like, not just the bin data? So that's a nice, really powerful tool to bring that together.
Thank you.
I haven't been monitoring the chat. Anything in the chat? Nope. Okay. Any other discussion or questions, requests? We're going to bring the microphone over to you so people at home can.
One of the things I was also thinking about yesterday is, do you have, if we're exporting images from what we're generating, like the top left, do you have are you like including also like OME TIFF as well? Like these multi-layer TIFF images where you could have more than one data stream?
Yeah, so not right now. That's actually a good idea. I like that. Typically, if you export a layer or an image, if you want the scale bar, it's doing screen resolution capture, really, when it comes down to it. Or you can save it as a high-res TIFF, which is as pixels. I always get people who complain to me, like, I saved it in high-res TIFF, but it's like this big. It's like, because that's the number of pixels in your image, is like 200 pixels by 200 pixels. It's going to be really tiny. And they put it on this giant monitor. So yeah, it's going to be small. But if you want to do multiple layers, we often we'll do an RGB multi-layer, right? There's also a another feature, which is the multi-fader here. And so what I can do is take, for instance, a grayscale in grays, and I can take my potassium map. Hopefully this will look reasonably well, and I can put that in the vertex. I'm going to overlay those together now, right? And I can there's even a little slider on the corner here to make this higher or lower contrast. I can fade these two signals together to see how they look, right? This is kind of like putting it together as a single image still, but I'm giving different color maps to each fader. Now, the one thing I've not liked about this so far is that I get this purple background everywhere on my low counts. That's the bottom of the color map. And when I use a color map like Jet, it's even worse. If I use a color map that has a black background, like it's called the standard gamma, I believe, which is really the maps color map, if you're familiar with APS data. Stefan Vogt's fault on that one. Again, it has that black background, so it doesn't actually give a weird color tinge, but it makes everything darker. And so what you really want to do is add a thresholding. And so that's the next layer of this. It's going to be a bottom threshold where you have a transparent layer if it's below a certain value, and then your color map goes from there up. And that's going to be, that's my last idea I had last week. It's not quite in the program yet, but it will be in the next version. But again, I think a multi-layer TIFF like that would also be very helpful to do that too. That'd be easy to implement as well. See, I have this little notepad right here that I've been hiding with all the things I need, and we're gonna go multi-layer TIFF.
Yeah, I mean, I was thinking, especially from some of the XRF data, and just because there's other tool sets outside of this that elemental data mapping would be super useful to, like these online tools, that if we had those overlays with mass spec imaging tools or something like that, where someone could pick what channel they wanted. And usually those are now in that open microscopy environment format.
Yeah, and they actually support the QTIFFs, which I know the biology people use for their histogram layers. And so it should be easy enough. I can already read those in.
Right.
So we should be able to read those in already, and then we can make an output format to support that as well.
And why are you making changes? I don't know that I saw in the color map Civitas as a color map.
It's there.
Oh, it's there. Okay. Okay. I had. Thank you. Well, not for me, for people that, have color vision deficiency.
And I will say, so this is also another point for, as much as I do love Jet, but it's very biased. And a lot of the other color schemes like RGB, everyone loves these RGB color maps because they are easy to do, right? But that is, people who don't see those, well, that's not a very good one to do. Get something that has something, yeah. You also can rotate the palette to a CMYK palette, and so it's a little bit better for people who are red-green difficulties. And all the palettes can rotate that way. So. And also in the same way, when we do multiple plots, you can choose different color palettes that have better sensitivity for bright field, low field. Any other questions? Matt? Yeah. So for everyone from home who may not have heard that on the microphone, Manny asked how to make a correlation plot, region of interest from the correlation plot. We have that data here. I'm going to come back and change our color mode here to none. Now just a boring green plot. I can come back to my map and say I want to know what the relationship is of this little corner of the stem. If you forget, you can always go to the help screen and get the help here. But we're going to use the shift. I'm going to hold down shift. And for those of you who have use the toolkit. We know we have to hold it down and leave it held down, not just release the shift key. Hold it down until you finish. And we're going to draw a region here. And when I'm done with that region, I'm going to double click and it will close the last box. You don't need to make it match perfectly. You just find the last one and double click. And then we say, in this case, we're going to make a mask, right? Now, I can also say, get the MCA or the mass to charge or the FTIR data from that little region as well. I can even do both if I want. I don't want to draw that over again. It's like often drawing on an image is not precise and you don't want to do it 4 times. You want to do it once. So you do it once. But in this case, we're just going to mask it. And there, it masks it out right away. I can come back to my correlation plot. If I go to color and use the highlight mask, that's the region I just highlighted right there. And it may be better if I then said, well, how did that correlate with sulfur phosphorus or potassium? And you can scroll through the different correlations to see how that region correlates. Another thing that I often come across, I'm not sure if I have a good data set to look at it here. We'll try this one here. Often people want to go like, well, how good is that correlation, right? You know, what's the slope of it? What's the R value on it, right? So I can say, draw a line. Oops, up, and see, now I found a new problem. Okay, so you can't do that right now. It'll be fixed. See, this is what happens to me all the time. Regression on the correlation plot. Okay, fine. This is what happens when you update versions. So anyways, normally it would draw a line here and give you a regression. And you can even go to multiple regressions because often, you know, particularly when we have XRF data, say we have arsenic and iron, we might see that there's 2 big lines, two major correlations. If you fit that, you get one line that goes in the middle and tells you nothing about anything, right? And so you can do multiple correlations and get multiple fingers to fit that and fit those all together at once. Anything else? Nothing new in the chat.
It's probably pretty obvious, but I guess it's easy to save off a text file of your spectra, right? You want to plot it somewhere else.
Yeah.
Just,
Almost every one of these regions here have a save function or an export function typically. Export right there, for instance. Because much as matplotlib looks okay on Python on a screen, it's not publication quality stuff. I don't want to spend all the time to make it to be export to publication quality because everyone has a different idea of what publication quality should be. And that shouldn't be my job, I don't think. So you're right, exporting is key. All those plots have an export function on to dump the data out. You can paste it into anything other than Excel typically to make your plot, whatever flavor you like best, or you dump it into Excel and then copy it somewhere else, but it just puts it on the clipboard.
There's a question in the chat. Can you export correlation with the highlighted area? So I can replot the highlighted area.
If I remember right, it should, every region that's a color will come out as a different column in the export plot. If it doesn't, it will by tomorrow.
And saving images, any format?
Yeah, so
formats?
typically you can export the display. So again, it does screen resolution, basically does like screen capture for you automatically in the area. That gives you all your annotations on it though. So if you have highlighted plot markers or scale bars, those will all come out in that image. And you, depending on the extension you put on it, it'll do JPEG, bitmap, TIFF, whatever format you want out, it'll save it in. If you also want the highest resolution, rather than if you have a large map and the screen resolution is cramping your style and not high enough, if you do the save as high-res display, it'll save out into a TIFF file as pixel. So in all preservation. And it's great for big files, and everyone complains on the small files. It's like a postage stamp. Those people remember what mail is like. Postage stamp. Okay. Okay. I think we'll end there and join our break, right? We're about 10:30 for that.
Yeah.
Oh, user meeting. Oh, yeah. I will also promo while I'm here. Thanks, Joss. The SSRL user meeting, particularly if you want to see more of SMAC. We have a lovely meeting in Menlo Park. But there will be another all-day SMAC demo going through not just multimodal stuff, but a lot of the other basics and other image processing stuff. And every recommendation that I've heard today will probably be in there by then. And it'll be also some hands-on. So we'll actually ask people to install SMAC and have some data sets that everyone can follow along and play with at home or away. And that will be September. It's the Sunday before my birthday. So September 22nd on a Sunday. I think we're going to try to do I'm going to see if I can convince them to make a Zoom out of it too. And so if you are crazy enough to want to spend your Sunday afternoon Zooming with me and SMAC, you can do that too. If I don't make it official, I'll make it unofficial. So
Kristen is asking, is that in person? Is in person only?
So that is a part of the SSRL users meeting that will be in person. And as Sarah was just asking, I'm going to try to make sure that we have a official or unofficial Zoom broadcast as well. I'm hopefully we'll make it official because I'm sure all our user admin wants to track all the good numbers of everyone who's rushing to the workshop. But if not, I'll post my own Zoom. Nothing else.
I'm not sure if Roloff caught the date, but he was asking when is the SMAC demo again and where?
And that will be the 22nd of September, which is the lovely Sunday afternoon and morning. 9 to 5. And yeah, so hopefully if you want more, you can get more SmackDown for the entire Sunday there. If you look at the SSRL's user meeting, you can probably register for remote for that. It will be also in person. And if you don't hear about anything being broadcast, spam me with email and I'll see what I can get set up and give you links and send out links to people.